Today we're going to talk about turbulence some more, so we'll finish up everything else that I wanted to talk about turbulence. That's not true. There's a lot more that I want to talk about, but I'm not going to because it'll get confusing and boring real fast, and we'll get deep in the weeds. So I could spend like the next 4 or 5 weeks talking about turbulence and turbulence modeling, but it's only so useful. So we're going to talk about structure functions. The reason that I'm going to talk about structure functions is because of this 4/5 law. There are very few analytic results in turbulence, and they're all from the 40s. There's a couple that maybe came from the mid-90s. So there's not a lot of analytic results where you can write something down and say this equals this, and there's not a big proportional or a constant that we don't know what it is. So the 4/5 law is one of the few places where we can say this is a number, it's real, there's no hand waving here, this works. And it works. And then everything else we have to hand wave from there. So the rest of the structure function lecture is waving hands. Then we'll talk about the Reynolds stress, which is doing the same perturbation theory that we did before, but this time we don't get to throw out the nonlinear term, and we'll see how bad that is. And then we'll talk about how to deal with that in the way of engineering models. Okay, so structure functions. So we did correlation functions Thursday, where we talked about Rij equals Vi at x, Vj at x plus r. We average over x so that this is just a function of r. Now Rij is a function of just the magnitude of r because of isotropy. And we said a bunch of stuff about this. So this is the correlation function, and it's the product of two things. The structure function is the difference of two things. So S2 of r, now again, this is the magnitude of r. Because of isotropy, the function only depends on the magnitude of this separation between 2 points. This is equal to the average of the velocity at a point x minus the velocity at a point x plus r. Absolute value, raise that squared. So this is very similar. This is a very similar function. What's the difference between this thing and this thing? I mean, it's pretty obvious. I mean, there's a minus sign here and there's a multiply sign here. But that's the only difference. I mean, I squared this one, but this one's already squared because I'm doing that multiply. They're the same thing. If I have, let's call this V1, I'll call this V2 just for shorthand. This is equal to V1 minus V2 squared, and that's equal to V1 squared minus 2 V1, oops, V2, does that look familiar? That's just this guy, plus V2 squared. But what's V1 squared? V1 squared is a quantity that we know. This is just the RMS Mach number. So this is, we'll call this sigma squared, and we'll call this one, this is the same thing. This is also sigma squared. Why? Because it doesn't matter. I'm averaging over all space. So if I start with, so if I'm averaging over every point in the box, every point in the box plus some distance is good. If I average over everything, it's going to give me just everything again. Doesn't matter if I call it one to the left. So these are both give me just, and this is just a number that characterizes the turbulence, minus Rij, is 2 Rij. So the structure function and the correlation function really give us very, very similar things. The only reason that I'm bringing up this new thing is because there's a really cool analytic result about this that I'm not going to derive because the derivation is kind of awful. I've actually only gone through the derivation twice in my life, once in class and once a couple of years ago, and I was like, how does this actually work again? And I got to the end and I'm like, that was terrible. Because it's long, so basically all you do is you take this, you integrate by parts a lot, and employ a bunch of vector identities and things like that. So I'm going to skip the derivation, but I'll tell you what it is. So this, let's talk about this for a second. This goes like v squared. And we talked about how v squared depends on the separation, right? So in our turbulent cascade, I'm going to draw this picture a lot. We have injection. We have dissipation. And we have the inertial range. So in the injection scale, this is a boundary condition. This is how you're dumping energy into the system. So this is whatever you feel like doing. You are God in your universe, in your physical experiment. You have a knob and you can set up what the injection scale is. Now, okay, if your experiment is I'm going to measure the turbulence in Chesapeake Bay, then this is fixed by the problem. But the turbulence doesn't care. The turbulence and the fluid dynamics behaves mostly in this inertial range. This is where the v dot grad v term dominates, and this is where the interesting physics happens. The dissipation range is where the Reynolds number gets small, and here molecular viscosity takes over again. In this inertial range, we showed, and I want everyone, so there's a bit in the homework, show this thing. I want everyone to make sure that you're really solid with this. I'm not going to go through the derivation again. V goes like L to the 1/3. So V squared goes like L to the 2/3. Let's call this R. I did it with L before. Let's call it R. I'm mixing notations a little bit here. So L and R are kind of equivalent. So V squared goes like R to the 2/3. That's this structure function. So we can make a generality about our structure functions. We'll call our structure functions SP of R. This is equal to the average of V at X minus V at X plus R raised to the P power. Now, why would I want to do that? Let's talk for a second about moments and how you get stuff out of them. So if I'm taking, no, that's the sticky one. I don't want that one. I want this one. So why would I take higher moments? Because you learn about the rare fluctuations. You learn about what else is going on. So if I'm looking at the average of A x, so A is some function. If I want to know the average of A of x, say I have some this one has some intermittent, very large, very rare spiky things. So the average of A is just what everybody's doing. This is like maximal socialism. This takes all of the points and brings them in together at the same level. So it gives you this measure of what everything is doing. A squared of x, that's going to give you a bigger value because it's going to more heavily weight the rare fluctuations. And also, if you have negative fluctuations, those become positive fluctuations. So those get wiped. The negativeness gets wiped away. But the square picks up the more rare fluctuations, but measures everything. But if I take A to some large power, 47, I'm going to raise everything to the 47th power. These things, these rare fluctuations, these rare peaks, are going to be so much larger than everything else. They're going to dominate what this average is. So by looking at higher order moments, you get different information about what's going on in the box. How rare are the fluctuations? Are the fluctuations extremely rare? Are the fluctuations extremely common? Are they huge and everywhere? Are they tiny and spread out? So you can learn that by taking moments of the equation. So we want to look at what what the structure function does, SP of x. So let's stop for a second and let's think about S3. So that's why we want to care about this pth order structure function. Yeah.
If you could take infinite number of moments from a function, what would that give you?
Then you have if you are able to take all of the moments, then you can reclassify the function from just the moments. So if I have everything, then I can go from the moments to the function itself. That's a big if, because I don't. But if I did, then I could reconstruct everything. And this is a result from probability. So if you know all the moments, then you know the function as well. So S3 of x, I'll just write it down. It's v of x minus v of x plus r cubed. And this one is special. Now, I said over here, we expect this to go like, to be proportional to r to the p over 3, which is 3 over 3, which is just 1. The camera is not in the right spot. That's a little better. And it turns out, and here's where, if you're interested, email me and I'll send you a PDF that has the proof in it. I think that everybody here now has the skills to go through it. It just takes a long time to get through everything because it's a very complicated derivation. It turns out this S3 of r x S3 of r equals minus 4/5 epsilon r. Now, when I did this for S2 of r, I said this was some constant c times epsilon to the 2/3 times L to the 2/3. Right? That's what I said v squared was. Well, that's what I said v squared was, which was related to S2. But S3, there's no constant. It's just a minus 4/5. And this is one of the very few analytic results in turbulence where you can say, okay, I've got some turbulent mess. What can I actually say about it? You could say this, and that's kind of it. You could say the second order structure function goes like p over 3. So so that's cool. Now that we understand this, so we know that S2 goes like L to the 2/3, and S3 goes like L to the 3/3. What's S4 do? It goes like L to some other exponent. This exponent is weaker than p to the 3. And S5 goes like L to some number that's even weaker than 5/3. So by the argument that we made, the hand-waving argument, you would expect S4 to go like L to the 4/3 and S5 to go like L to the 5/3. But they don't. They're softer functions than that because, so if I look at P versus N, so this is S2, this is S3, so we know what those are. This P goes like, P over 3. And we'll put that in quotes. So that goes like 2/3, that goes like 3/3. 4 is weaker than that, and 5 is still weaker. So the scaling looks like this. So this is the exponent on the scaling. The exponent up here, that's what I'm drawing here. And what this tells us is that when we're looking at high order moments, there are a lot fewer rare fluctuations than we expect. Because turbulence doesn't fill space. The dissipation doesn't fill space. The tiny little structures that turbulence makes doesn't fill space. It's intermittent. This is a very important function of turbulence, and it is one of the edges of human knowledge. we can't really say as much about intermittency as we want. It's got to become a fractal, and I'm going to skip all the fractal theories because it's lots of hand waving. But if one could figure out a solution to what how S of p should behave with scaling, then you would be famous. That would be a really great success. So let me sum up what I just said. Okay, so I'm going to stop talking about structure functions. Here, okay, so the structure function is this. The important takeaways that I want you to take away from this is 1, SP of R equals what it is, V of X minus V of X plus R to the P. 2, one expects that S of P should go like L to the P over 3. This is what you expect from hand waving, from dimensional analysis. And it works for 2. Oh, I'm sorry, I should call this, let me be a little bit less hand wavy. S2 of R should go like proportional to R to the P over 3. I'm going to try to use R for everything. S2 of R, we know, goes like some constant that's like 1.5 epsilon to the 1 to the 2/3 R to the 2/3. That one's good. S3 of R is minus 4/5 epsilon R. That's factual and true and very useful. C, S4 of R, SP bigger than 3 of R, goes like R to the Q, which is less than P over 3. Because you don't get as many, because the turbulence is intermittent. Did I get everything on there? How does this chalk show up? I guess okay. So the structure function and the correlation function are real similar. So you can say similar things about the correlation function. Does anybody have any questions about that? Does that make sense for the most part? So the correlation function is an increasing function of R. So what does this mean? This means that if I huck 2 bottles into the ocean, they're going to separate. And the velocity of their separation is going to increase as their distance increases. And that's why the mixing is so, in turbulence, is so effective. So, all right, let's look at the Reynolds stress for a second. So, let's write down Navier-Stokes. We'll write down the momentum equation, which is equivalent to Navier-Stokes. D rho v is minus d by dj of rho vi vj minus p, plus p delta ij minus mu dj vi. So this is the second derivative diffusion term. It's the second derivative because we've got a dj and a dj here. Here's my nonlinear term, and here's my pressure term. And again, we're all incompressible. I put that up there mainly for myself because a lot of what I do from day to day is compressible. So I don't get to throw out the density terms, but here we get to. So we're going to assume that things are incompressible for now. So that means that rho is constant. It also means that dj vj is 0, so that's also handy. So what we want to do is we want to say I have some velocity is some mean velocity. That's like the water is going down the river on average, plus v prime. It's not going in a straight line down the river, it's wandering around with some chaos. So we have a mean and a deviation from that mean. This is the same thing that we did when we linearized stuff before. And we'll also say that P is P bar plus P prime. P is nicely behaved, so that doesn't give us nearly as many problems. When I drop this into here and average, what am I left with? So let's say, I'm going to say d by dt of rho v bar plus v prime, and then I'm going to average that. So this equals minus d by dj of rho v bar plus v prime, v bar plus v prime, this one is I, this one is j, plus p bar plus p prime, delta ij, plus nu d by dj of v bar plus v prime. All right, straightforward. Let's flesh out what this thing is. This is vi bar vj bar plus vi bar vj prime plus vi prime vj bar plus vi prime vj prime. That's just FOIL of this thing. So now I'm going to average this term too. So okay, if I have v equals v bar plus v prime, and v bar is the average, then if I average all of this, then I'm left with v bar equals v bar bar plus v prime bar. V bar is a constant with respect to however I'm doing this average. Now this could be an ensemble average, and it's still constant. But so this is just this, and the fluctuating part, by definition, is 0. Or the average of the fluctuating part. If I average the fluctuating part, that goes away. So we'll do that. We'll average everything. So let's look at this first term. We're left with d by dt of rho v bar. The v prime goes away. Equals minus d by dj of rho vi vj bar bar. That's this one. Plus this one, I've got a rho times vi vj prime. What happens if I have rho vi bar vj prime? What happens when I average that? What is that equal to? If you're having trouble doing this in your head, think for a moment about what an average is. What is an average? Somebody yell something out. What do you know about averages? It's a magical function that we just turn the crank on without thinking about. That's not true. How do you find the average of, like, say I've got 10 things and I want to find the average. What do you do?
Add them up, divide by 10.
Add them up. I don't care about the dividing by 10. You can take care of that. You just add them up, right?
Depends on the average.
So we just average. So an average is just an integral. Full stop. An average is just an integral. You're just adding stuff up. So I'm just adding stuff up. So this is an integral. This is a constant with respect to that integral. So this is the integral of rho v bar v prime dx. Maybe it's an ensemble average, and this isn't dx. I'm doing something different. But this is still constant. So this is equal to rho v bar average of v prime, which is 0. So this term goes away. So this term we keep. This term goes away. This term, same thing. It's got a fluctuating and a not fluctuating. It goes away. This one, however, has 2 fluctuatings. There's no reason for me to throw it out because it doesn't go away because it's not the average of the fluctuating things. So my Reynolds averaged term has VI plus VI VJ. This is a term that looks just like what we had before, but now has bars here. Now we have another term, rho vi prime vj prime bar. This term is a pain in the ass. Many people's careers are spent around trying to make this term behave or fake this term. Let's go, what else is here? So that's all for the nonlinear term. Then from the linear term, I've got a p bar and a p prime. That's just going to become p bar, delta ij, and then the last term, again, I've just got two of these things, and the second one's just going to be disappear. So dj vi bar. So now I've got an equation. So what did I do? What did I do? So I averaged Navier-Stokes to get an equation for V bar, the average. So this is, yeah.
Remind me why we changed from mu to nu.
Muscle memory.
Okay.
So what I wanted was an equation for the average flow, and what I get is an equation for the average flow that looks just like Navier-Stokes except for this extra force term. So now we have to talk about what this thing is and how to deal with it. What does it mean? What is this term mean? What is... Do I need anybody here? No. So I write down my Navier-Stokes equation, and I write d by dt. Let's just write Euler for a second. Vi plus Vj dj vi. This term is Vi getting pushed around by Vj. So I have some little parcel of gas. It has some component Vi in one direction, some component Vj in the other direction. Vj is pushing Vi in that direction. Does that make sense? Vi is also pushing Vj in the I direction, but that's the symmetry. So when I write out the Navier-Stokes equation, I have a term that goes like Vi bar Vj prime. What is this? And there's a d by dj. There's a rho, but I don't really care about the rho. This is the mean flow pushing around the fluctuations in the flow. So I have some mean flow of the river, and it's carrying my little fluctuations along with it. So this is like I've got a boat, and I drive it through the river. The boat kicks up a wake. The river carries the wake down the river. That's this term. That averages out. Or I can view this term as little fluctuations pushing and trying to alter the mean. That doesn't work out for them, so this term averages out to 0. But this term, dj vi vj bar bar, this is the mean flow pushing around the mean flow. That's problematic if you have any kind of simple flow. But if you have a more complex flow, then you have the large-scale flow interacting with itself, just like in Navier-Stokes. This last term, dj vi prime vj prime, is little stuff interacting with little stuff to make big stuff. So this is little fluctuations interacting with themselves to make larger scale mean flow. So this is tiny things taking over. That's not tiny. Maybe these are large. Let's put tiny in quotes so you know I'm lying to you. This is tiny pushing tiny and making large. So your fluctuations are pushing your fluctuations around and making large scale flow. So you're getting structures from the chaos of the flow. These things are chaotic, but they can give you large-scale motion. They can give you bulk motion. I don't know how to deal with that in any way other than saying this is a thing that's going to happen. It's going to be hard to deal with. So how do we deal with this? What we do is we pretend it's a diffusion. Why? Turns out that it works pretty okay as a diffusion. So we got to fake it now. Okay, how do we fake it? So this is called the Reynolds stress. And it's equal to Vi prime Vj prime, average of that. And it's a tensor, but its tensorness doesn't really affect us too much because we don't understand anything about how it is. So we're going to make it not a tensor immediately and wave our hands. So how do we deal with this nonlinear term? The best way to deal with it is with direct numerical simulation. So with direct numerical simulation, and I'll talk a little bit more, I'm going to list a couple of things and I'll talk about more of them in detail for a second. Direct numerical simulation simulates d by dt of Vi plus Vj, Vj, Vi equals minus 1 over rho grad P plus nu del squared Vi. So we simulate this whole equation. And so how do we, anyway, I'll talk about how we do that in a second. Second, we can deal with the Reynolds average Navier-Stokes. I'm not writing all that out, or RANS. And with RANS, we treat the Vj, Vi prime Vj prime bar as a diffusion. And it's going to look like d times dv dx. That's how diffusion works. Diffusion is the second derivative, and then there's some constant in front that tells you how fast it goes. Okay, so what's dt? What gradient do I use? Do I use u here, or do I use u bar here? What do I use for this? Well, I want to use something that I can measure, so we'll use the mean equation. So we'll use the mean velocity, because I can measure the mean velocity. Two things about this whole process. V bar is measurable. You can measure the mean velocity. You just sit there and integrate. You just take data for a while and average everything up. So you can measure that. V prime is not measurable for a couple of reasons. One, you can't extract that data. Say I've got a river and I want to know what V prime is for every point in the river. I have to measure the velocity at every point in the river. There are 10 to the 23 atoms for every cubic centimeter of water. That is a god-awful number of measurements that I need to make. I don't know how to make 10 to the 20 some odd measurements, or 10 to the 40, however many I need to make. I can't measure this, so it's not really an accessible quantity. And you'll talk about this when you get to quantum mechanics. Some things are not measurable and some things are measurable. And the fluctuating quantity is not measurable, maybe in less fundamentally obscure ways, but it's not a measurable quantity. So we want to base things on things that we can measure from the simulation, from the experiment, from our model. So the first thing that you can do is directly simulate. So what happens when you directly simulate? Oh, sorry. Let me flesh out this outline a little better. So I'll talk about direct numerical simulation, then I'll talk about Reynolds average things. And I'm going to talk about zero equations, and this is mixing length. And I'll talk about one equation. This is the K model. And then I'm going to mention the existence of other things, but I'm not going to show them to you. They stop being things that you can really understand quickly. So, okay, let's talk about direct numerical simulation. So, what I want to do is say my goal is to understand the flow patterns around the back end of an airplane wing. So, I got an airplane. It's got a wing. Airplanes taper at the back, otherwise they get huge drag. They taper at the front too for the same reason. Say I want to simulate this. What I'm going to do is I'm going to take a model of my box, or a model of my plane, and I'm going to split space into little boxes. And then I'm going to say each one of those boxes contains some velocity of some fluid, and I want to know how the fluid behaves in those boxes. Now, I could not treat them as boxes, or I could treat them as points. There's fundamental and very subtle differences between the two, but it doesn't matter. I'm going to take my object and I'm going to break it into little pieces. And I'm going to simulate those little pieces by saying full Navier-Stokes. D rho v dt equals minus rad f minus mu del squared v. Realistically, we pack this into here, but regardless. So I'm writing this explicitly as two terms to point out the fact that we're treating this del squared as part of the flow equation. So how do I do this? How do I treat this? One way to deal with this is to average. So here's now my space. And I'm going to have an airplane in here, but I'm going to break it into little tiny chunks. And we'll wrap out an airplane. Maybe they're not cubes. I could make them tetrahedra, which are more useful in some ways, but harder to deal with, but not a lot. But they're a lot harder to draw. So we'll draw squares because they're easy. So this is zone I. This is zone I plus 1. So I'm going to integrate this. I'm going to discretize it by integrating between I minus 1/2 and I plus 1/2. And J and K will do this in 3 dimensions, but I'm lazy, so I'm only going to write 1. So when I integrate, if I average the whole equation in space, let's average it in time too, from some time t to some time t plus delta t. Because it turns out we can't be continuous in time either. We have to break things into chunks in both space and time. When I do the time integral of this, I'm left with d, let's call momentum pi. We'll call our zone I. So this pi, I, is the integral of from minus 1 I plus 1/2 to I plus derp, from I minus 1/2 to I plus 1/2 of rho v of x dx. You can make this 3-dimensional easily by just adding 2 more integrals. So d by dt of pi I, well, I'm going to integrate this from t to t plus delta t as well. So, and this is a full derivative. So this turns out to just be pi at, I want this capital pi, of I at n plus 1 minus pi of I at n over delta t. So this is what my time derivative turns into. It's just a difference. So now what I want is pi of n plus 1 equals pi of n plus this flux term. Well, the spatial averages of the flux, so I do a spatial average of the flux, which gets rid of this grad, and a time average, which I have to take care of internally. So my Navier-Stokes equation turns into pi n plus 1 equals pi n plus fi plus 1/2 minus fi minus 1/2 times delta t over delta x. So now we have a discrete equation where we've broken things into space, and this is what it kind of looks like. It doesn't really matter a ton. My point is that we've broken my thing that I'm trying to compute into little chunks. Maybe it's an airplane, maybe it's a molecular cloud, maybe it's a whole galaxy. I'm breaking it into little chunks, and I have these average quantities that I'm going to integrate through time. The details of all of this are super fascinating, but kind of time consuming, so I'm going to way pants past it. The important bit is I'm breaking up space. Now, what kind of flows can I compute? So one of the results that I showed you the other day, and you will do again for class, is the ratio of the injection scale to the dissipation scale. It goes like the Reynolds number to the minus 3/4. I said that wrong. This way it goes like the Reynolds number to the 3/4. So this is the size of my box, and this is the size of my zone. The zone that I'm computing needs to be a lot smaller than the dissipation length scale so that I can resolve the dissipation length scale. But let's say that I need the zone to be the dissipation length scale. How many zones can I fit into a computer? How many pieces of information can I possibly fit into my computer? Kind of large, but the bigger it gets, the harder it gets to deal with. So a typical number of zones that I can use for a simulation is about 1,000. So one of the things that I do is, as I study turbulence in clouds of gas, so I just have a cube of outer space, and I dump energy into it, and I watch how the turbulence behaves. I can get away with about 1,000 zones across. So that means 1,000 cubed zones for the whole box. That fills up, I use 32 supercomputers, and for an aggregate 4,000 processors, and it runs for about a week. That's something you can do. It's not too painful. It's pretty easy to get a supercomputer if you know what you're doing. But it's kind of a headache. So that's 1,000 cubed. Bigger than 1,000 cubed starts to become very difficult very quickly because the cost goes like the number of zones to the 4th power. Because if I have 1,000 zones across, that's 1,000 cubed zones in 3 dimensions, and my time requirements gets more restrictive as my simulation gets smaller. So L over LD is realistically about 1,000, which means that I can simulate a Reynolds number of, I put the 3/4 over here. So if L over LD is 1,000, then the Reynolds number is like 10 to the 4. Now, what was the Reynolds number of the flow across an airplane wing? Reynolds number of a flow across an airplane wing was about 30,000 is the number you should have gotten. I wasn't super careful about that, but you should get a number of about 30,000 to simulate an airplane wing. That's not enough. This is only 10,000. I need a factor of 3 more, and this is not actually covering the inertial range. So even with a simulation that is a large pain in the ass, I can't really cover my airplane wing. And if I want to do something like a molecular cloud, where the Reynolds number is 10 to the 12, all hope is gone. So direct numerical simulation, where I break space into a bunch of cubes and I simulate everything, including the viscosity term, and I explicitly cost that. That's really the best thing to do in a lot of ways, from an accuracy point of view, because you're really putting your hands on what is the turbulence doing. But it's really limited in what you can simulate. So direct numerical simulation is great. Let's use a different color. Is the best, but it's limited by resolution. So if we want to simulate something, so say I want to do something more modest. Say I only want to do 256 zones across, so my simulation is 256 cubed. For this, for a simulation of this size, I use 4 expensive desktops, and it takes, again, about a week. Here, for 256, the Reynolds number I can get is only about 1,600. And so this is like, if you recall, we got a value of about 1,000 when we were drinking water through a straw. That's a pretty mild simulation and not very interesting. If we want to do something that has a more aggressive flow, 256 cubed is not enough points. Now, I just wrote a paper using simulations of this size, so it's not a useless size, but it's hard to really get, if you really want to understand the viscous dynamics, it's very difficult. So what can we do instead? So we want to do something more complex, where we say simulate a very large explosion where the Reynolds number of the flow is 10 to 6. Then we have to do something else. So what do we do instead? I'm out of time. Good. So we have d by dt of rho v I bar equals minus d by dj of rho vi vj plus p delta ij, and we have a bar over the bar here, there's a bar here, there's a bar here, minus rho vi prime vj prime bar. Now the bar here is over both of these things, and here there's a bar over each one of these. And I want you to think about this bar as an integral. So think about this thing as integral of vi over stuff. And this one is another integral of vi v other stuff. So I can't just put them together. This one is one integral, vi vj d stuff. So they look pretty similar. I mean, the only difference between this term and this term is a little notch in this line, right? Which is a little gap in the way I wrote it, but they're very different terms. So let's talk about this thing. So we're going to model this as a diffusion term. So, how do we say? Oh, come here. So what we say is that vi vj prime prime bar is equal to some turbulent diffusion times vj vi bar plus vi vj bar. Now, these are really different quantities. This is the mean quantity. So we're trying to model the effects of fluctuating quantities acting on fluctuating quantities as gradients of the mean quantity. Does that make sense? seems like kind of a, like the jump here isn't obvious. Like these are two V's and this is a derivative. But the behavior is pretty similar. So the behavior of turbulence is to diffuse things and to spread things around and to smear stuff out. So treating it like a diffusion is not unreasonable. So now what's D? You ready? D could be lots of stuff. I have a huge amount of freedom with what I pick for this D. It's a giant knob. So the first thing we can do is to simplify this and say, okay, so let's say we're modeling flow across a boundary. So this is, say, like the side of a ship, and we're trying to model how water moves past the ship. We didn't do the wall turbulence, which I probably should have done, but we find out amount of time. So what you find if you're looking at flow past a boundary is there's a thickness called the boundary layer where the flow is turbulent, and the turbulence falls off as you move away from the wall. So we'll just deal with this, and everything that we're going to deal with, we've got one direction y and one direction x, and y is away from the wall, and that's where the things are changing. So I'm going to have a gradient in my fluctuation just because the turbulence is going to be here next to my wall. It's not going to be up here away from the wall, because the wall is what's being dragged through the fluid or whatever. So we're going to rewrite this instead as some new turbulence times dv I bar dy. And now we can just say dv dy because we really only have one. We'll deal with this in one dimension for a minute. So what is vt? So we're going to, or new t. So what we're going to assume is that the turbulent velocity is going to be some, so okay, remember when we talked about viscosity the first time? And I said viscosity is equal to the RMS velocity of the particles times the mean free path. I should have made a homework on this because I think that would have been useful. I still can. I'm not done giving homeworks. Just to drive this home. So viscosity is a velocity times a length scale. So it's a typical velocity, and you're pushing that velocity around by a typical length scale. So remember how we did viscosity in the first place. So I've got some large flow here. I've got some smaller flow next to it. The viscosity is how much velocity do I carry over this distance. So it's a similar kind of model. So the viscous, the turbulent viscosity is going to be some turbulent velocities times some mixing length. Okay, I just invented two new parameters. Yay! So the turbulent velocity, the typical turbulent velocity, we're going to say is some mixing length times du bar dy. Okay, so now my turbulent viscosity is going to be L squared times du bar dy squared. And then I plug that back in. And now, okay, I had to make a couple assumptions, and I did this circular thing where I said, okay, nu of t is something times my mixing length. Something is my mixing length times my gradient, which is the thing that I described up here, but that's all right. I just need some estimate of the turbulent size scale. So we're going to say the turbulent size scale is however much the mean flow changes by the distance. That's going to be whatever's left over. So I have gradients in my mean flow. That's going to give me my fluctuating flow. That's this assumption here. I have my fluctuating flow being transmitted over my mixing length. That's this assumption here. then we get that my turbulent viscosity is going to be my mixing length, and this is a knob, but if I have a boundary condition like this, I can measure what this is. So this is something that I can get my hand on if I understand the physics of the simulation or the situation a little bit, but it's a knob that you have to understand. Times a gradient in the fluid, which I can measure pretty easily. So then my whole mixing length theory says that, so what mixing length theory says is that the Reynolds stress is equal to some diffusion. That's a pretty common thing. We're going to make that assumption a bunch. The mixing length says that the turbulent viscosity goes like the turbulent velocity, we'll come back to that, times the mixing length as a knob. And the turbulent velocity is the mixing length, which is a knob, times the gradients in my flow. A little circular, but it eliminates all the unknowns. So now I have a theory that only has one knob in it, and it's something that in principle is a characteristic property of this situation of the flow. So zero equation, mixing length, we say that nu of t equals ut du bar dy, and ut equals L mixing du bar dy. So this is nice. So mixing length is nice because you can write down analytic answers. So that's the good part. The downside of mixing length theory is it's total BS. However, it works okay. It's an okay thing to do. Another application of mixing length is in stellar convection. This is where a lot of this was developed in the first place, is in stellar interiors. So if you look at how a star works, and I think hopefully because teaching physics of stars next fall, if anybody wants to take it, they'll go through this in horrifying detail. So in a lot of stars, you have the nuclear burning down to the center. This nuclear burning is so hot it causes convection.
Is that supposed to be the radioactive symbol, or is it?
Yeah, it's pretty
okay.
bad though. So we have the nuclear burning, which drives the convection. It's just because it's hot, and if the temperature gradient from here to here is a lot, then it'll start to boil, just like Rayleigh-Bernard convection, like we did before. But then up here, where the gradient's not so much, then we have this radiative zone where the photons just kind of go through and the fluid isn't kicked up. But we have this transition layer here. This is smooth circular flow. We can deal with that. This is radiation. It's not, we don't really know how to deal, or we know how to deal with that. That's not very complicated. It's just radiation. This layer here has some mixing length, and there's some mixing region where you get a turbulent region in between these two regions. So the mixing length theory is really useful here because I have all of the things that I need. I have a good understanding of the gradients of the velocity and the size scales and the structure. So mixing length theory for stellar structure is very useful. It's not perfect, but it is an extremely useful model. Then, from there, we can get a lot more complicated if we like. I'm going to show you one, and then I'm going to stop. So mixing length theory is useful. It's useful if you've got boundary flow. It's useful if you've got like a stellar interior. It's useful if there's like one dimension and you can characterize the gradients by a single parameter. So mixing length is very useful kind of BS, works pretty good in certain scenarios. If you have a more complicated scenario, you don't have an obvious boundary layer to deal with, and that's really when mixing length is useful, is when there's a boundary and a thickness of the turbulence. If you have something worse than that, like an explosion, where, say you've got a supernova that goes off, that's going to be violent through the whole supernova, and the whole thing is turbulent. So you might need to be a little bit smarter. So what we say instead, again, we say that VI prime, VJ prime bar, this is the Reynolds stress. Remember, this came from trying to ask what the mean and fluctuating terms of the equation are. We're again going to say that this is nu T times du bar dy. Perhaps we're still dealing with boundary flow. It doesn't matter. If you need to generalize this, one can do that. I don't need to do that right now. So what we're going to assume is that the turbulent diffusivity is equal to the square root of the turbulent kinetic energy times the length scale of the structure. Now this length is a knob, but it's less important that it's a knob. In mixing length theory, that knob does basically everything. That knob is the turbulent diffusivity. Here, I've got a knob, but I've got this other thing, square root of k, where square root of k, where k is 1/2 vi prime vj prime over bar. Well, that's too complicated. No, I'm sorry. That's a tensor. Vi squared, that's a scalar. It's a scalar, so it's nicer to deal with. It also characterizes all the fluctuating turbulent energy. So it's not the whole stress, it's just the trace of the stress. Does that make sense? The trace is just you add up the diagonal. So the stress is a tensor, it's a matrix, it's got two indices. The kinetic energy is just the sum of the stuff on the diagonal of that thing. But we now need an equation for this, because this is a flow variable. So these are quantities that the flow is naturally going to produce. I can't make things up, so I need to have an equation for this. This is why this is a one equation model. Mixing length theory is a zero equation model, because I don't have to make any new equations. I don't have to close it in any other way. I'm closing it by waving hands really aggressively. Here I'm going to close the equations by I totally didn't talk about the closure problem. Damn. Anyway, I'll talk about the closure problem in a second. What do I mean by closing the equations? Okay, so by getting all the moments, if I want the first moment, this spits out something that goes like the second moment. Now, I have this thing, and I want an evolution equation for k, which is vi times vi. Well, what's that? So we need dk dt. Now, okay, most of the time when I use k, I mean wave number. Here, I mean kinetic energy. dk dt is vi prime dvj dvi prime dt prime over bar. All right. Yeah. Now I know what this is. dvi prime dt is dv dt minus dv bar dt. I got that one over there. Oh no. Oh, I erased it. So this is Navier-Stokes, and this is the Reynolds average Navier-Stokes. This one picks up an extra term. I'm going to skip a couple of bits. When you actually do this, and you average it, you get a term that looks like the product of VI, VJ, and VK. You get a triple product. This is the third moment. So now I need an equation for this. And when I try to get an equation for this, I pick up something that goes like VI Vj, Vk, Vl, prime, 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 over bar, I get something that goes like the fourth moment. And if I try to get an equation for the fourth moment, I get an equation, it spits out the fifth moment, so I need an equation for the fifth moment. So if I really want to calculate all of the moments of the Navier-Stokes equation, I can't, because each one needs the next one. So I can't ever stop. So by closing the equations, I mean we're just going to decide, well, okay, one of these equations we're going to make up some crap. Then we're going to stop. We're going to close the process. That's a spooky noise.
Yeah.
What do you think? I saw them, they're rolling something out on the, so we're underneath the patio, right? And I saw them doing something, rolling out some big rolls of stuff out there earlier. Anyway, so the closure problem is, if I want the second moment, I have to have the third moment. If I want the nth moment, I have to have the n plus 1 moment. So we need to stop. So how do we close these equations? So when I do this, I get this equation. So I'll write out what the actual equation looks like. So if I do this, then I'm left with dk dt. Remember, this is the fluctuating energy. This is the energy that's in the fluctuating fields. Is equal to, let's see, minus d by dxj u vj prime vi over 2 plus p prime over rho prime prime prime. So I got a vj, a vi and a vi over 2, a p prime over rho minus vi vj prime prime over bar du bar I dxj, oh no, I, that was an I too, minus nu d vi prime squared over bar dxj. So what is this? What do all these things mean? Did I get everything? Oh, I missed one. Plus nu times d squared k dx squared. So if you stare at this for a while and you think about it, then we can make a bunch more approximations. So now I've got, I mean, I'm looking for my evolution of my k. It depends on k, but this is just diffusion. So this is just spreading things around. I understand that. That's pretty good. This, here I've got these products of all these fluctuating things. I don't know how to deal with that. And here I've got a product of fluctuating things as well. So so we can rewrite this. So we make assumptions about what each one of these terms does. So we'll say that ui prime uj prime times dui dxi, that's this term. We're going to assume that this is just some turbulent diffusion times nu I ut. And the turbulent diffusion, again, is just k to the 1/2 times L. So we'll make an assumption for this and stick it in there. And similarly, we'll make another assumption. I'm going to put these notes on, put the notes where I got this from online. But I take this equation and I'm left with something that I can't solve because it has all these terms in it that I don't know what to do with. And I try to get an equation for, say, this term. It's going to have 4 velocities in it. So we need to make an assumption. We need to truncate the hierarchy of moments here and make assumptions for what each one of these terms are. And I'm low on time, and I'm not going to get too deep into the weeds. But when you make assumptions, then you have an equation for k that looks like this. dt of k, now this is the subgrid energy, equals minus d by dy of nu t, this is this nu t that we're dealing with. Turbulent is k to the 1/2 times the mixing length. Nu t over sigma k, and sigma k is another parameter. Times dk dy plus nu t d squared k. Sorry. Du bar dy squared minus c dk to 3/2 over L. So what I've done is take an equation that I don't know how to solve and wave my hands for each one of the terms in it carefully. So this term, we've seen terms like this. This is the gradient of a velocity times like an energy. So this is the flux. This is turbulent energy pushing turbulent energy around. This term is a diffusive term, and these two terms make a dissipation term. So what we need to do is model production, advection, and diffusion of kinetic energy. So we have to stop getting new equations, and we just have to say, what's in this equation that we need? How can we fake that using gradients of the mean flow? And we wind up with something that looks like this. And what it is that doesn't matter a ton right now because we're running out of time. But this equation has pushing production and dissipation in it. But I have another equation, and it's still kind of BS. So we go back to our list of how do you simulate turbulence? How do you get turbulence? So direct numerical simulation is the best thing that you can do, really, but it's very expensive. So it gets really expensive really fast. So it's hard to use for the things that you want. So we use Reynolds averaging instead, and you can use mixing length, which is really nice because you can just write down the answer, but also kind of BS. Or you can use a 1-equation model or a 2-equation model, which are nice, which are more accurate. Better than mixing length, but they're a lot more complicated. Because now you have more equations that you have to solve, and that's a headache, because I just want to solve the Navier-Stokes equation. But my model says, well, you have to invent a new equation and model that too. Yeah. Does anybody have any questions on, yeah?
So is the further you go out with the final thing, the better it becomes? Like the more equations that you make?
Only if you're doing it right. So in principle, yes, if you're doing it well, the more equations is a better solution. But there's a lot of places where your approximations can break down. So if you're doing something like really simulating the wing of an airplane or a nuclear explosion, they use more equations typically. But you have to do it right. You have to do it smart. All right.
How many equations would they do for that type of stuff?
I think 7 is one of the more common ones. Let me see. Hang on one second. I might have it right here. Oops, no. What? Oh, no, I don't. I got to track it down. So, yeah, so they'll use 7 equation models that have a lot of extra crap in them. But those are for people who really know what they're doing.